what we have here is an example problem in AutoCAD. It's going to develop shear and moment diagrams for it. So if you take a look, zoom into it, this is going to be the same format, by the way, that you're going to have in the two problems that you're going to be doing as part of this assignment. So what we have here is we have a beam diagram that shows the information on the loads and the supports for that beam. If you take a look at it, we have a distance of 20 feet for the beam, and it is supported on the left, point A, and supported on the right, point B. Point A is what we call a pin connection, while point B is what we would call a roller connection. On that beam, we have two types of loads. We have one, which is a 4,000 pound concentrated load at one point, and then we have what's called a distributed load along the entire length of the beam that is equivalent to 650 pounds per foot on that beam. These, once again, is called concentrated loads and distributed loads. We also need to locate where those loads are. So right now we have the concentrated load is located 6 feet from the left support. Now on these problems that we're going to be doing, we've also drawn in here a couple of things that are going to be valuable in determining what the loads or the forces are on this beam, as well as developing our shear moment diagrams. We have up here, we have our three equilibrium equations. We have the sum of all moments must equal 0, the sum of all vertical forces must equal 0, and the sum of all horizontal forces are 0. Also, when you see the letter V, that represents shear. When you see the letter M, that represents moment. Our units on these problems that we're going to be doing are in feet. So 6 here represents 6 feet, 14 feet, and 20 feet. What is also extremely important when we apply these equations is that we know the sign convention for the force. So as an example, an upward force, which might be the reaction force at the support, is considered positive, while a downward force is considered negative. So when we put it into the equations, we'll know whether to use a negative or a positive value for that force that's coming in, or for that amount that we're going to be putting in. As an example, your 4,000 pound force here would be considered a negative force. Your 650 pound per foot distributed load is considered a negative force. Why? Because they are both acting in the downward direction. We're also going to select a sign convention where forces going to the right are considered positive and forces to the left are considered negative. The same thing applies for moment forces. A counterclockwise force, moment force, is going to be considered positive, while a clockwise is considered negative. So let's go ahead and let's get into the problem right now. We're going to go back to our model space where we have the same thing we were just looking at into there. And what we have here is our 2-pin connections, and we have all our conventions located into there. So the first thing that we're going to do is we are going to basically create what we call a free body diagram. The free body diagram is going to start in here. It's simple line, horizontal line that represents the beam, left and right. And here we have our two supports, A and B, on the right side. The next thing we're going to do is we're going to apply our forces that we had in the beam diagram to our free body diagram. As you can see, we've got our concentrated load and our distributed load indicated the same way. But instead of these symbols that we have here for our supports and our connections, we are then representing them as both a vertical force and a horizontal force. Now, because this is a pin connection and it does not allow the beam to move left or right onto that, the resisting forces or reaction forces are both in the horizontal and vertical direction. So we have Fxa, which is at point A, and the vertical force is Fy at point A. So X represents your X axes and Y is your vertical axes in the Cartesian coordinate system. On the right-hand side, remember that we had a pinned connection at point B. Well, the pinned connection allows for horizontal movement on that, so we do not have a horizontal reaction force to it. We do have our vertical force reaction at FYB. The next thing we'll do is we're going to once again determine where those forces are coming down on our free body diagram. So we put the exact same dimensions that we had on it. Our concentrated load is 6 feet from the left, and that leaves 14 feet for our 20-foot beam, the full length. So the first thing we're going to solve for is going to be our horizontal forces. We only have one, which is FXA, so what we're going to do is we're going to select, let me go ahead and pan this down a little bit. We're going to select our equation, which is going to be the summation of forces in the x direction. Right in there. And since we only have one potential reaction force, we know that Fxa is going to be equal to 0. So again, as we had mentioned previously, when you have no horizontal forces applied, which we do not in this situation, you can ignore this. This just represents that we solved for that problem on there. The next thing we're going to do is we're going to solve for our vertical forces. We need to solve for Fya or Fyb. So we're going to use our second equation here, which is the summation of forces in the vertical direction. So the first thing we need to do is put our symbol down here. Summation of forces in the y direction is equal to 0. The next step is to sum all of those forces that we have in our free body diagram. So we know that Fya plus Fyb, they are both positive, minus any negative forces, such as our concentrated load of 4,000 here, plus our distributed load on here times the distance of that distributed load must equal 0. So we continue developing our equation here, and we end up with Fya plus Fyb is equal to 4,000 plus 13,000 pounds. So we know that Fya plus Fyb is going to be a total of 17,000 pounds. The only problem is that we have two variables and we need to solve for one of them. For that, we can use one of our other equations here in terms of solving for one of those values. So the next thing that we're going to do is we're going to go ahead and we are going to solve for our moments. So the first thing we will do, hold on one second, first thing we will do is we are going to put our equation right here for our summation of moments must equal 0. Next thing we're going to do is we're going to create our equation here. So the summation of moments, and remember, a moment is a force located a specific distance from where you are taking the moments. So what we're going to do is we're going to take our summation of moments around point A into here. So any forces that are coming down to the right are going to be considered moving clockwise, and if you remember our conventions in here, that is going to be a negative moment, while any reactions or any forces going up are going to be considered positive. A good way of taking a look at this is if we were summing all of the moment forces around point A, is if you were to put your finger on there and hold it down, which direction would the beam be turning? Because of the 4,000 pound load, it would be turning clockwise. And our reaction at Fyb would be pushing the beam up, which would be rotating it counterclockwise, so it would be a positive force. So let's begin with our force, a positive force in here of Fyb times the distance that it is from where we're taking the moment, the summation of moments, which is point A. So we got a positive FYB times 20 feet minus our 4,000 pound load, concentrated load, 6 feet away from that moment where we are taking the force, and then another minus 13,000 pounds at 10 feet located, and all the summation of those forces should equal 0. Now the big question is, how did we get this 10 feet? We have a distributed load, which is 650 pounds per foot, all the way across the entire beam. Well, what we do in order to solve this calculation is we take that concentrated load, or we take that distributed load, which totaled 13,000 pounds at this point, and what we do is we then assume an equivalent concentrated load point. When you have a uniform distributed load, that point will be at the center of that distributed load. Well, in this case, the load is 20 feet across, so our location around point A is going to be 10 feet away. So what we can do is we can take our 13,000 pounds, located now, because that is the equivalent concentrated load, 10 feet from point A, where we are taking our summation of moments, and we can add it to our equation located right here. Our next step is to continue solving the equation. So we have FYB times 20 feet is equal to 24,000 foot-pounds plus 130,000 foot-pounds for our equivalent concentrated load. Now notice all we did at this point was we took these two values and we moved them to the other side of the equation. So we took a negative 4,000, and to balance it off we put a positive 4,000 on the right hand side, coming up with that equation. The next step is we're solving for FYB times 20 feet is a total of 154,000 foot-pounds, and then finally we come with our reaction at FYB. Our vertical reaction is 7,700 pounds. So we can add that element right here, that value, to our free body diagram. So what we've actually done right now is we've solved for one of the two variables in our previous equation for the summation of vertical forces. So all we really need to do now is to basically calculate and finish calculating our reaction forces. So let's pan this up just a little bit right in here. And let's continue with our equations. So from our previous summation of forces, we knew that FYA plus FYB was equal to 17,000 pounds. So what we're going to do at this stage is we're going to substitute the 7,700 that we found in our moment equation for FYB. So we have FYA plus 7,700 pounds is a total of 17,000 pounds. We go to our next value, and now we solve for FYA, and we know that is 9,300 pounds located right here. So what we've done is we've solved our equations and we've solved our reactions on this beam. So we know that our left support is supporting 9,300 pounds, while our right support at B is supporting 7,700 pounds. So our next item that we're going to do is we're going to start developing what we call our shear diagrams and our moment diagrams. We're going to start with our shear diagram first. So what we do is we begin laying it out, the full expanse of the beam. We're going to lay out two guidelines, left and right, and we're going to have a baseline here, which is V, which is shear, where our shear force, which is what's going to be shown in our shear diagram, is going to be 0 at that point. The next thing we need to do is we need to indicate guidelines of where any critical point might be occurring on the shear diagram. Now we have that concentrated load, which is located right here, and we've indicated that with this line right in here at 6 feet over. Now we're not going to take our equivalent concentrated load, because in our shear diagram we want to represent this distributed load exactly as it is. So what happens is when we're moving from left to right on our shear diagram, we want to express the increase in the load of 600 pounds per foot. We are not going to use our equivalent load at that point. So the next step is to go ahead and draw our shear diagram. Now if you take a look at one of the first things that we're going to do with our shear diagram is wherever that event takes place, we're going to have a vertical line going up and down if it's a concentrated load or if it's a reaction at that point. So we start at the left of the beam, and we're going to start with reactions and loads and forces as they go towards the right. So here we know that we have a reaction of 9,300 pounds. So we start from 0 and we draw a vertical line, 9,300 pounds. Now our units here are equivalent. So when we put in 9, that's going to be 9,000. So 1 is going to be the equivalent of 1,000 pounds. Okay, so 1 unit is equivalent to 9,000 pounds. So to draw that line vertically at this point, I would have input 9.3 in the vertical direction. Now, if this was only our point load or our concentrate at that point, we would have no change in our shear until we got to that point. It would be a horizontal line. And you will see that in some of the other examples that you're going to see. But in this case, it's a distributed load. So what ends up happening is that's going to be coming down at an angle in here, equivalent to the distance that it's traveling, plus the load that is being applied to it. So 1 foot over, you would have a 650 vertical load, which means down. The next point it would be, at this point, would be 1,300, and so on as we go. That creates this slope for this angle, for that line. So that will continue at that specific slope based on the weight per foot times the distance that it's going across until it reaches the other event right here, which is our, if we pan down just a little bit in here, or zoom out, you will see that is where we have our 4,000 pound load. There again, it's going to become a vertical line coming down 4,000 pounds coming down, and then we continue again with our, with our distributed load coming across in this direction. So the next step that we're going to do is we're going to go ahead and put some values to that. And as I mentioned before, this slope of this line is based on the 650 pounds per foot times the distance onto here. So that is going to determine that the distance from here to here is 3,900 pounds. At 650 pounds per every foot, that angle will bring it down to 3,900 pounds lower than our 9,300 pound value. Then we apply here, we apply our next load, which is our 4,000 pound load, which is the vertical load, concentrated load coming down there. And then we continue again with our slope for our distributed load coming down at the same value that we were coming down before. Now, if everything has been drawn correctly, then what we're going to do is we have our FYB reaction force here on the end that is going to be pushing up at this point. So that value in there should end up being 7,700 pounds. We also need to evaluate what this distance is in here. So that would be one of our next values that we're going to be putting in there. So once we know that distance and we know how much this traveled in here, then we can basically help solve for our maximum moment later on. So we have our vertical component of this triangle here. We need to solve for our horizontal component right in here. So our next step is going to be to try to find x. So we know that x is going to be 1,400 pounds divided by 650 foot-pounds. That gives us an x value of 2.1 feet in that direction. So now we've located where x is going to be and where our shear basically is 0. We have 0 shear at that point. And the reason that's important, because our maximum moment, that's the maximum stress inside of that beam, is going to occur where shear is equal to 0. They're inverse to each other at that point. So let's continue with our equations in here. And there is the minus 7,700 that I was talking about at the final point in here. The next step we're going to do is we are going to solve for what we call Vmax. Vmax right here is the maximum shear stress that is occurring on that beam. It usually occurs at the supports in most instances, not always. But here we know that our shear at this support was 9,300 pounds, and that becomes our maximum shear stress on this beam. The next thing we're going to do is we're going to go ahead and create our moment diagrams. So let's go ahead and zoom right into here. And what we're going to do is we're going to go ahead and find once again where any events might be occurring in here that might affect our moment diagram. One of them would be this vertical drop in here where our concentrated load, and the other one, which is extremely important, is where shear force is equal to 0 is going to be our maximum moment line. So that's what we need to solve for. What is our maximum moment so we can draw our moment diagram. So what we need to actually do is we need to create a separate free body diagram around what would be considered this point, which is our maximum moment. So that's what we're going to try to solve for with this free body diagram for the moment around point P, which is going to be our location point for where shear is equal to 0. So let's take a look at what forces we have. We know there are no horizontal forces in here. We have two forces that are coming down vertically on the beam at that point. One is the concentrated load and the other one is the distributed load in here. So what we need to do is we have established where that concentrated load is going to be, and we have all the distance to the vertical reaction in here, which all of these forces need to counter. The horizontal forces need to be countered also. So the next step is to use our equation for the summation of moments around point P, so we call it MP. And we solve for the equation. We know that all of the forces, all of the moment forces need to equal 0. So we have our reaction force, which is M in here, needs to counter all of the forces which are going against it. So we have 4,000 pounds coming down into here, which is going to cause a counterclockwise motion. Okay, and if we recall up in here, our counterclockwise motion is a positive. So this value here is a positive value, plus the 600 pounds per foot times the full distance here. So that value will be our value for that distance in there, times the distance in here. Now, this distance is what we would call the equivalent distance to where that load would be. So that is the equivalent concentrated load location for the 650 pounds per foot over a span of 8.15 feet. And then finally we have our reaction force in here, which is a negative number because it is going clockwise. Remember our sign conventions. Times the distance it is away from where we are taking our moment. And all of that needs to equal 0. So our next step is to go ahead and solve for the equation. And we find out that our M in here, which is the equivalent to maximum moment, is equal to 45,608 foot-pounds. So we know based on our vertical location here that our maximum moment is going to occur where our shear is 0 right along this point, and that is going to be our location for our maximum moment right there. So the next thing we need to do is we are going to go ahead and solve for our how to draw our shear diagram right into here. And as you can tell, it's a parabolic curve, or it's a curved surface into here. If there was only concentrated loads and not a distributed load, these lines would be straight lines. It is because we have a distributed load onto here that the curve occurs. One last thing that we should note is that because there is a significant event happening here, which is the concentrated load of 4,000 pounds here, you would probably get what we would call like a kink in the curve. It would not be a smooth curve going all around. You would have a small kink into there. So we've done a number of things in here. We've solved for maximum shear, we've solved for maximum moment, and we have solved for the reactions on both sides of the beam where the supports are located. So what you're going to do is you're going to go ahead and show all of these items in the problems that I'm going to give you, and you're going to follow this exact same procedure that we did here. It's going to be a little different depending on the problem. Now we're going to go from our model space to our layout space, and this should look very much like this, except for obviously it'll be a different equation. Your shear diagram and moment diagrams will be different, but they should be located on the left, and all the calculations should be located on the right. Put your name at the top and the date that you've put onto it, or when you completed it, and then all you need to do at this point is, you are in paper space now, is you need to go ahead and go to print. Continue to plot a single sheet. Everything should be set up already the way that you want it. Go ahead and preview it onto there. It is a B-size sheet. That's already been set up on the example DWGs and the problem DWGs I sent you. And it should look like this. No borders. I don't need any of that. All I need is your name, the date, and the work and the diagrams shown into here. And that is it for these two problems that you're going to do for shear and moment diagrams.